Logistic regression is a machine learning algorithm for classification. In this algorithm, the probabilities describing the possible outcomes of a single trial are modeled using a logistic function. So let's just bring this example in. We have maybe some cats and dogs, and we want to determine the weight at which we would suspect that this is going to be a cat versus a dog. And so we'll take our data points for training and then modify this logistic function. Okay, maybe move it over, widen or narrow it. Okay, so I'm going to make it, okay, that's the intercept, the B naught. And you can see this equation right here. There's the B naught, and then I can make this just a little bit steeper and then maybe move it over to the left. Okay, so this is going to be the probability that it's going to be a dog, which would be a 1, or a cat, which would be a 0. And we're going to move this so that it basically performs this, it creates this boundary between the two. And we're going to use the Python functions to do this, but also we're going to code it from scratch in Python. So it's not a very complicated algorithm, and I wanted to be able to have you have some understanding of this so that you can, when you're using some of the packages, you can understand what's happening with it fitting the data and then predicting as well, and some of the strengths and limitations of this. So let's just look at logistic regression example here. Here are two Crescent data sets that are moving together, and there you can see the X's is when there's a misclassification. And you can see the blue shaded line that basically is the logistic regression predicting that it's going to be a blue dot if it's on that side of the line. And if it's on this side of the line here, on the upper quadrant, then you say it's going to be an orange dot. And there you can see the probabilities as well. You can see the train and predict times are very fast, and the size doesn't change. Okay, it's very memory efficient as well. Although the accuracy is not as good as some other methods, the speed and low memory requirements, and just if they have many variables and maybe one or two are very good predictors of an outcome, logistic regression can work very well. It's also often used as an output layer for something like a neural network to translate a continuous value into a discrete value. So logistic regression is designed, although it says regression in the name, it's designed for classification, and it's most useful for understanding the influence of several independent variables on a single outcome. Also, one disadvantage is it assumes all predictors are independent of each other. So you get these very linear relationships. Basically, it's trying to draw a boundary that it becomes linear. And so to use this with sklearn, you can just import, and I'll show an example of this with some number classification with logistic regression. So here's an example. Let's just go ahead and get the code for this. And if you come into a notebook, you can import it. If you just type load and then type that address, okay, and then hit enter, then it will load it in. So let me go ahead and just do that again. Okay, it'll load it from the website, or you can copy that in. So we're going to first of all just import sklearn datasets. That's going to be our those are going to be our numbers. We'll do a train test split, and then we'll have a plot as well. So if you just run this, you'll see the number classification here. Here it's predicted that it's a 2, and you can see the number. These are the pixels. So these are all of the independent data points. You have this number of pixels by this number of pixels, so 8 by 8, and you can see the result. All right, so I'm just going to run this again, and there's a predicted 1, and run it again, there's a predicted 7, And so you can run this multiple times just to see how it's predicting and if it misclassifies or does a good job in predicting the outcome. So this is just a number digit with logistic regression. Alright, let's come back here. I just want to walk through just another example, and we're going to code this one ourselves for this next example, where we use only Python code, not a machine learning package like scikit-learn or sklearn or others. So we're going to create a logistic regression classifier. We'll use the blobs test code to evaluate the performance of the code with any number of features. So we're going to start with 2, and then your assignment basically is to take that code and to make something that's generalized, any number of features, and we'll test this here. Okay, so number of features, just increase that, and then test your code to make sure it works. So let's go ahead and get this code. Alright, and I'll create a new cell below. And we can load this one in. For some reason, when you put in the HTTPS, it doesn't work for me. So I just load it in and then run this, and you'll see the pair plot. Okay, so that's, random state. If you change that, you can get a different result, slightly different result. And you're welcome to do that if you want to change the random state. But just to start, let's go ahead and just keep this one with a random state of 12. Okay, so let's go ahead and just code this up. We're going to start by, first of all, okay, so we want to import a couple things. First of all, just split it. We had this imported from before, but let me just go ahead and import it again. This is going to be our model selection. We'll import train test split, and then let's go ahead and divide this into train and test sets. And we'll just have our data dot values, and I'll have my test size equals 0.2. Alright, and then if we look at train, for example, we can see that's just an array of values. And if we look at the length of train, okay, it's 640, and then the length of test is 160. So there's our 80-20 split that we want for the train and the test set. Okay, let's insert another cell below. Now what we want to do is go ahead and predict based on these beta values that we have. So I'm going to just move this over here, and let's, as we talk about this, I'll just write out the formula, and we'll see if we can implement it. Alright, so the formula that we're going to use, you saw in that calculator example, is P equals, and that's going to be 1 divided by 1 plus e to the negative b naught, or beta naught, plus beta 1 times x1 plus beta 2 times x2. Okay, so there's our formula that we're going to implement, and we want to just create something that can return the predicted value, the probability based on the values of beta and the x1 and x2 values. So I'm going to also just use the Python index, which is going to be x0 and x1. So we need our exponential function, and I'll do that from math. We'll import exp, and then let's define our predicted function, and let's have our row and our beta. So we're going to have a data row, and then from this we could have x1, x2 like this, or if we just keep it general, we just say x equals row 0 to 2. Okay, because we might have the label in there as well, so we're just going to take just the first two elements. Alright, so y hat, this is our predicted probability. Okay, it's going to be, actually this is going to be a thing that goes in the exponent. Alright, that's going to be beta 0 plus beta 1 times x0 plus beta 2 times x1. And then we'll return 1 divided by 1 plus, and this is going to be exp of negative y hat. Okay, so there's our function that we need to just be able to predict what the probability is. We're going to return the probability. And then we'll, if it's, you know, on one side of that 50% or the other, we can then convert it to a discrete number. All right, now we want to update the coefficients, and this is the formula that we're going to use for beta 0. Beta 0 is going to be, for one iteration, it's going to be beta 0 plus the learning rate. Okay, I'll just do that as L rate times the error. All right, and then times y hat, and then 1 minus y hat. And then for our coefficients, this is going to be, you know, the beta I plus 1, or, you know, beta I. So that's going to be 1, 2, 3. And then that's going to be equal to beta I plus this learning rate times the error in the predicted versus the measured values, and then we'll have the same thing, okay, times xi. Okay, I'm going to put that as xi plus 1, I plus 1. Okay, just because we're multiplying the beta 1 times x0 value. Okay, so there are update formulas, and we might use a learning rate, you know, that can be adjusted to help it converge. But we could start in this example with something like 0.3. Okay, and the error is going to be the difference between the measured label and the predicted label. So error is going to be equal to the measured label y minus the predicted label y hat. And then xi is our input feature. So we'll just continue for 100 iterations, and then we'll plot the loss function as we go, just to see how well it's doing. All right, so let's go ahead and just put all this into this logistic regression example here. Okay, and I forgot the colon at the end of this. Okay, so let's go ahead and just take this and go learning rate equals 0.3. We also need the number of epochs. Those are the iterations. We'll set that as 100. All right, and then let's just record our loss function. That's going to be zeros, and we'll have for every iteration, we'll keep track of that loss function, or that's our objective function that we're going to say how well, like the sum of the error or the sum of squared error, or something like that, some metric that we're going to use to record how well we're doing. And then let's just start off with our beta values. And so this could be 0 times 3, like this, or if you want to just do a more traditional, okay, list, you know, these 3 beta values. Okay, so for one epoch in range number of epochs, okay, so we're going to go through one at a time. We're going to sum the error. That's going to be equal to 0 because we're going to keep track of it as we go through this. And then we'll go for row in train. We're going to operate on each data row individually. All right, and we'll go take our x value, and that's going to be row 0 to -1. So that's going to be 1 less than the end. So it's going to not include the label at the very end, and then y is going to be row -1. So in this case, our data is listed as okay, so this is going to be our x1, or I guess in Python it's x0, x1, and then our y value. And we're just going to take this as x, and then this one as y. Okay, and then we'll go on to the next one. So we'll go on to the next row and update with that one as well. So every time you go through an epoch, you're basically cycling through all of the data points, and you're having it update the beta values as you go. All right, so let's go ahead and just calculate now the y hat. This is our predicted value, and we'll use that predict function with the row and the beta values. Now what we want to do is come up with our error, and that's going to be y minus y hat, so the measured minus the predicted value, and then the sum of our squared error is going to be equal to error squared. Okay, let's go ahead and update these now. Here's our beta 0 value. This is how we're going to update it. We'll do a plus equals. So we'll have our learning rate times the error times y hat times 1 minus y hat. Now the next ones are going to be very similar to that. Okay, but they're going to have the index 1, and then the other thing they're going to have is just at the very end, they're going to be multiplied by the input. Okay, so let's go ahead and copy these, and we're going to do this just for 2 input features, and then we'll expand it to additional ones. Okay, and then we'll keep track of our loss function for each of these iterations. Alright, so let's go ahead and just run this one, and it looks like we have an error. Oh, okay, so we need the number of epochs. Okay, so I've trained it, and let's just go ahead and see the results. Alright, let's get our beta values. There you can see the intercept, and then the 2 coefficients, beta 1 and beta 2. And then let's also go ahead and just plot the loss function. Alright, so there's our loss function, so you can see the training as it went. You can see it asymptotically approached about 10 for the loss function. Okay, so that did a fairly good job, but let's go ahead and just come up with our confusion matrix now, just to be able to see how well this did. So we're going to round it, so if it's greater than 0.5, we'll say it's a 1. If it's less than 0.5, we'll say it's a 0. Okay, so let's come up with y hat, and then we're going to go through all of our test values. For row in test, we'll have y hat append, and we'll round what we come up with from our predict function with the row and the new beta values. Okay, so there's our test. And now let's go ahead and just plot the confusion matrix. So from sklearn, we'll use metrics. We'll import confusion matrix. And confusion matrix is going to be equal to confusion matrix with our test values. Now we want all the rows and just the very last column. So we just want the y values like we saw right here. Okay, so that's going to be our, we're going to say all of the rows. That's when we put in the colon. It means visit all of them. And then the very last one is -1. Okay, so that's those are our measured values, and then our predicted values are y hat. Now let's go ahead and just create a seaborne heat map. And we'll annotate it as well. Okay, so you can see how well it did on the test results. On those, you know, I think let's see, the length of that. Okay, we had 160 data points, and you can see these add up to 160. So when it was a 0 for the measured values, it also predicted a 0, and when it was a 1 for the measured values, it also predicted a 1. So it did fairly well. This is the one where it didn't do as well. You have 4 here out of that test set where it classified them incorrectly. So the measured value was a 0, but it predicted a 1. So we had a misclassification there. So now the next step is to make this general for any number of input features. So if you'd like to try it yourself, go ahead and just pause the video and try it yourself, and then I'll work through this you know, the rest of the way to make it more general. So if you had a function, you had any number of input features, and we'll go ahead and do logistic regression for this as well. All right, let's come back up here to the number of features, and I'll just increase this to 3. Okay, so there we have 3 features instead of just 2, and you know, I would need to visualize this in some way. Once you have more features, okay, let's see if I can even come up with that. Okay, so let's see, data frame. We have our data x1, x2, and then let's just come up with the third one. x3 equals features. Alright, so there are 3 features, x1, x2, and x3. Okay, so we still have 2 labels, 0 or 1, but now we have this third feature. If I wanted to have 4 features, I could just set that to 4. Okay, and you can see that it's just going to create additional columns and rows here in this pair plot. So one of the nice things about logistic regression, if there's a particular feature that's able to distinguish these two really well, like this one, logistic regression is going to perform really well because it can draw a line between these. There's a lot of separation, and it's going to perform fantastically. When you have a lot of overlap like this one, then it's not going to do as well, especially if there's some nonlinearity to those features. But all you really need is just at least one explanatory variable, one feature that can help you predict that label where there's good separation between these two. So for example, in the cats and dogs, maybe weight isn't a good feature to use, but maybe the color might be a good one. Okay, so let's come down here. We're going to just train test split these. That one can stay the same. All right, and then what we want to do is make this one, any number of x values. So I'll just go ahead and say to the end minus 1, and then we need to change our prediction here so that we say that it's equal to beta naught. But then as we increase the number of x's, okay, so for xi in x, then we're going to add to y hat. Okay, and then I might need to enumerate this as well. So let me get an I value there. Okay, so that's going to be beta I plus 1, and then beta I plus 1. Oh, I don't need this next one, and then I can just replace this with xi. Or I can put x bracket I, like that. Okay, so either one. All right, and then what I want to do is just return the same thing that we had before. So I've just made this generic so that it can accept any number of x's. Just run that just to load in that function. All right, now what we want to do is on the beta values, we're going to need 1 for every additional dimension. So we'll need to load in maybe the number of dimensions that we had. All right, so that's going to be the number of input features, or number of dimensions is 4. So this one is going to be equal to zeros. But then we want to multiply it by, let's see, that's going to be 1 additional plus the number of input features that we have. So that's going to create a beta list of 5 values that are all zeros. Okay, this one looks correct. Okay, we just have the number of x's. We've already adjusted our predict function. Our error looks good. And now what we want to do is just update these so that it can update it for any number of beta values. So let's do for I in range ND. And now we only need one of these, not all of them. So I'll just say I plus 1, and we'll have our learning rate, and then all the error and everything else stays the same. Y hat, 1 minus y hat, and then we'll just put xi in here. Okay, we'll train those for the 4. Now let's print out our beta values. Oh, and I think I may have made a mistake here. That's a lot of beta values. Oh, ND. Okay, ND plus 1. I didn't need all those extra beta values there. Okay, there are my beta values. Now let's go ahead and just plot the loss function, how well it learned. This one should be very fast. Okay, you can see that one feature where there's some separation. It learned, and you got almost 100% classification success. All right, let's go ahead and just run this one. We're going to test it. And now let's go ahead and do our confusion matrix. Okay, so this is our confusion matrix. Although we had 4 features, we still only have 2 labels. So you can see on the test set, it perfectly classified those. And so you can see here, 0, 0, no misclassifications on the diagonals. So let's go back to just 3. Okay, so maybe make this just a little bit more challenging. I'm going to just decrease this by 1. Number of features, maybe I change this to ND up here, equal to 3. And then number of features, ND. And then let me change this down here to get rid of this, so we make it more general just from the start. Okay, so looks like maybe I'll change the random state, make it a little bit more difficult. This one also looks kind of easy. All right, you can see the distributions. Those are very easy as well. Maybe I got to go through these and find a more challenging one just to see some misclassifications. Okay, this one's again very easy. This one would be easy for it to... Okay, so let's just keep going until we find one where it's going to be a little bit more challenging for it to do the classification. This one's a little bit better. This one still is going to be not too bad. But let's increase maybe the number of samples. Okay, so just a little bit of overlap. Run it again. We'll do our train test split. Here's our learning. See, it's going to take just a little bit longer. There's our beta values. Print our loss function. Oh, well, you know what? That one looked like it learned very well. Let's just see on the test to see if we got any misclassifications here. So we got no misclassifications. So it was a perfect classifier. That, again, was too easy. So let's go up there and just keep changing the random state until we get it to maybe have a little bit more overlap. You know what? That one's still, it's going to be very easy for it because, there's a separation. Again, all you need is just one input feature that has this type of separation, and then it becomes an easy classification. All right, and let's go ahead and just do a couple more just to see what we can find. I don't want to spend too long on this. I can let you go through that yourself if you'd like. Okay, I'm ready to stop, but maybe if you want to go through it yourself. Ooh, here's one. Oh, we were so close. There's that. Okay, so go ahead and go through those random states, and there are also some additional options that you can use on make blobs that can increase or decrease the standard deviation of those. So maybe we should do that. See if we can find some standard deviation. Okay, cluster standard deviation. I'll go ahead and just make that, instead of default 1, we'll just increase that to, increase the scatter, so it doesn't really matter. We don't have to get random state exactly right. We'll just increase this a little bit more. Let's just stick with 4 there on the random state and just keep increasing the standard deviation. Okay, that has some right here. All right, let's just go with that. We've already gotten our help on that. Let's go and do the train test split. There's our function. Let's learn. Get our beta values. We'll see if we don't level out at 0, so you can see the learning. So we did get just some misclassifications, not very many. It was a little bit more challenging as we increased that standard deviation for the classifier. So if you want to get any of the source code for this, I'll post this video as well here to the Machine Learning for Engineers page. And this is Logistic Regression programming, and there's all of the source code if you'd like to come here and grab that. And there's a couple additional articles. I felt like the Wikipedia article was also very good. It gave some additional examples about test scores versus number of hours studied. Also, I really like this one on how to implement logistic regression from scratch in Python. That one's also very good. So all of the examples, I'll post this link right here into the comment section and into the description, and then I'd love to hear your comments as well.